we have heard already many talks on many-body Anderson localization. So in this talk, I would like to make a step back and return to the single particle Anderson problem. And hopefully I will be able to convince you that there are still some interesting questions and interesting results that can be obtained for this problem. Okay, so we have heard already many times, and we have seen many slides similar like this. So Anderson model is a model for a single particle moving in a disordered potential. So the strength of the potential, the range of the potential is controlled by parameter W. And then we know that in three-dimensional case, we have a transition from extended to localized states if we change the strength of the potential. So we have quite good qualitative understanding of the physics of the Anderson model. But at the same time, if we want to understand it analytically, analytical results are quite limited, so they're limited to special situations. We understand very well the one-dimensional systems where we have a number of different techniques which allow us to calculate all kinds of quantities analytically. We also understand very well quasi-one-dimensional systems, and by quasi-one-dimensional systems I mean the system with it's like one-dimensional system but with a finite cross-section, or we can think about coupled one-dimensional chains. And here we have two very powerful approaches. One is the so-called DMPK equation, and I'm going to discuss this equation in this talk. And the second approach is a nonlinear sigma model, which I'm not really going to discuss in this talk. For high-dimensional systems, we have the phenomenological scaling theory of Anderson localization. The nonlinear sigma model can be still derived for high-dimensional system. However, we don't know how to solve it. And the best thing we can do is just use a kind of renormalization group approach, a perturbative expansion of the sigma model in the metallic regime. So we can say that generally we don't have a good analytical theory for Anderson localization for high-dimensional systems beyond metallic regime. And the goal of my work is to develop such a theory. And in this talk, I'm going to present you only some first steps towards this goal. So I'm going to discuss the most natural orthogonal symmetry class and weak disorder, but arbitrary dimensionality. So the first part in this talk, I'm going to look at the statistics of delay times. So here I'm going to consider the scattering setup where we have a sample with one lead attached to the one side of the sample. And the second part is work in progress. So here I have only some preliminary results. And in this part, I'm going to talk about statistics of transmission eigenvalues. All right, so since I'm interested in the weak disorder limit, I can, from the very beginning, to go to the continuum limit and consider a problem formulated in continuum. So we have just so we have a single particle moving in a delta correlated random potential. So the strength of the potential sigma can be expressed in terms of the density of states and the scattering mean 3 time. And so R is d-dimensional vector. So the first component I will denote it by X, and the rest, the d minus 1 dimensional component, I will denote it by rho. So we have a sample which has a length L in the X direction, and all the other dimensions will be equal to M. So what I'm going to do is to attach a perfect lead to the one side of the sample, and then we will have a quantizations of states in this disorder-free region. So we will have some transverse eigenfunctions. So for example, in the case of Dirichlet boundary condition, they will be given by standing waves. So they characterized by some energies n. And in this way, for a given energy, we get a finite number of propagating channels. So this number will be denoted by n. and it can be calculated in terms of the width m and the energy that we consider. So that we will have a scattering, n by n scattering matrix. So the matrix is unitary as it should be, and additionally, because we have a time reversal symmetry in the problem, the scattering matrix is symmetric in this case. So another object that I'm going to introduce is the so-called Wigner-Smith time delay matrix, which is basically the derivative of the phases of the scattering matrix with respect to energy, or more formally, it can be defined in this way. And I will try to convince you that this is actually the object in this for this setup, not the scattering matrix itself, but rather this Wigner-Smith time delay matrix. So it's a Hermitian matrix, and again, because of this additional symmetry in the problem, in this case, the metric is symmetric. So the eigenvalues of this matrix Q, the so-called proper delay times, so this will be the main objects of the interest in the first part of the talk. So what I would like to do, I would like to understand how the properties of the scattering matrix and the properties of the Q matrix change when we change the system size, when we some slice of the length delta L to our sample. So n, this small n, is basically the length of the sample measured in this small length increases delta L. So it's a discrete variable which measures the length of the sample. And then we can ask how the scattering matrix for the sample of size L and size L plus delta L, how they are related. And in order to find the relation between them, first of all, we need to work out the scattering matrix for this small slice delta L. And this can be done. So the answer can be written in terms of the potential part of our sample. So the standard representation of the scattering matrix is like this. So we have four blocks, reflection and transmission blocks. And in this case, each of them can be expressed in terms of two matrices. So one is matrix V. So as I said, so this matrix is basically the matrix elements of the potential calculated with respect to transverse eigenfunctions and averaged over this small length delta L. And the second matrix appearing in this expression is matrix Q. So this is diagonal matrix of longitudinal eigenvectors. So once we know the scattering matrix for this layer delta L, we can use the composition rule for the scattering matrices and derive the relation between the scattering matrix for this sample L plus delta L and the original sample as L. And this is how this relation looks like. So the function f introduced here is defined here. And this matrix A is basically this matrix which appears here. So it's a matrix consisting of potential and matrix Q. Okay, so this is the relation for the scattering matrices. And the next step, I'm going to differentiate this relation in order to derive the relation for matrix Q. So I differentiate it with respect to energy. And in this way, one can find an explicit relation for recursion relation for matrix Q. So here I don't want to give you details because it's quite a lengthy expression. But the point is that it's rather simple linear relation. And the matrices U and delta Q appearing here, they can be expressed in terms of matrices, scattering matrix S, the matrix of the potential, and this diagonal matrix Q. Okay, so one can check that both relations, they preserve corresponding symmetries. And so this relation, they hold actually for any strength of disorder. So up to this point, I don't need to make an assumption about the strength of disorder. And they're also very suitable for numerical calculation because when you deal with scattering matrices, the matrix size that you need to diagonalize is much less than if you deal with the Hamiltonian. Okay, so now I'm going to consider this limit of weak disorder. And in this limit, we have separation of scales. So we know that in this limit, the much larger than the Fermi wavelengths. And for this reason, I will argue that we have a separation of variables. We have a fast and slow variables. So if one analyze these recursion relations for and Q matrices, one can see that the change of the scattering matrix itself and the eigenvectors matrix of Q, which I will denote by O, so this change is controlled by parameter delta L over lambda Fermi, while the change of the eigenvalues of Q is controlled by a different parameter delta L over L. And because we have this difference in the scales, so the first two variables become fast variables and the delay times become slow variables. So that means the fast variables will be randomized very fast, and they can be integrated out. And in order to do this, I'm going to use the following assumptions about S and O matrices. So I'm going to assume that these are two statistically independent random matrices. They have zero mean value, and the variances just given by this. Basically, the variances are uniform. Yeah. Yeah. To some extent. Well, we will see it. We will see what we will get. So, yes, it will enter my answer, but in a very simple way through the number of channels. Okay, we can discuss it later. Okay. So, okay, so these conjectures I mentioned motivated by these recursion relations, and okay, let's look at the numerical results. So whether this is true or not. So so the first two relations, well, I didn't show the numerical results for this first line because, well, it's very good, so nothing to discuss here. But there is something to discuss about the second line. So what you can see here is the matrix elements of the scattering matrix, and you can see that indeed they are uniform, and except for the diagonal, but on the diagonal this is what we expect. There is a just factor of 2 difference according to this formula, which just follows from the symmetry of the scattering matrix. If you look at the matrix elements of O, well, then we can see there is some deviation from uniform distribution, not very strong, but there is some deviation. And it might be the case that this deviation is important, but I'm going to come back to this point in the second part of my talk. So now I'm just going to assume that we can neglect this deviation from uniformity. So this is the system size, L equals to M equals 480, and this corresponds to the yeah, this is the dimension M. M determines the dimension of perpendicular slice. So it's a square sample now. Okay, so now the next step is to derive the Fokker-Planck equation for the distribution of delay times. And so the change of the matrix Q at each step generates some change of the corresponding eigenvalues, and then we can use the standard procedure to derive the Fokker-Planck equation for the distribution of delay times using the assumptions that I mentioned. So, and this is the result that was derived assuming that the number of channels is much greater than 1. So what I've done here, I introduced some new notation. So the delay times are now measured in the units of the scattering times, and the lengths are measured in the units of the mean free path, and AD is some geometrical constant. So what we can see that, well, it's non-trivial Fokker-Planck equation. There is obviously some non-trivial interaction between different taus, and so this distribution function should contain full information about delay times. But equation is quite complicated, so instead of trying to solve this equation, what I would like to do is to introduce another quantity, which is a simpler quantity, the density of the delay times. So it's can be obtained from the full distribution function by integrating all the variables except one. And so then, again, there is a standard way to transform the equation for the probability distribution to the equation for density. And this is how the equation for the density looks like. So, while on one hand we have now a simpler object which depends only on one variable tau, but on the other hand you can see the equation that we get is a complicated non-linear integral differential equation. But hopefully there is, fortunately there is a way to deal with such equations. So the first thing that can be done here is to introduce the Stieltjes transform of the density defined in this way. So the new function f is a function of complex variable z. This function is analytic in the whole complex plane except for the real positive axis. And then on this real positive axis it has a jump. And so using this formula for the jump one can derive equation for f. And what we get is the Burger's equation for this new function f. So it's a nonlinear equation, but it's just differential equation, so we don't have any integral term anymore. And once we can solve it, we can restore the density just using this simple formula. Okay, so the next step, if you want to solve it, we can use the so-called Hopf-Kohl transformation. So this is a nonlinear change of the function f, and here also change the function, the variable z, introduce a new variable s. And so in this way one can transform the equation for f into equation for u, and now it takes just standard form of a generalized diffusion equation. So it's a linear equation, so we have some differential operator on the right hand side, and that means we can find now eigenfunctions and write down the solution as a linear combination of these eigenfunctions with corresponding exponential functions of time. So in this case, okay, the time is played by R. Okay, so what is the spectrum of this problem? Well, it turns out that we have a continuous spectrum, and so it can be parameterized by parameter mu, which is positive real number, and the corresponding eigenfunctions are Whittaker functions, which are labeled by these two indices. N is the number of channel, and mu is our eigenvalue. And additionally to this continuous spectrum, we have an isolated eigenvalue lambda equals to 0, and this eigenvalue corresponds to the Whittaker function with index 1/2 here. So obviously lambda equals to 0 corresponds to stationary state, so this is a stationary state in our problem. Okay, so once we know the complete eigenfunctions, we can write down the solution for arbitrary R in terms of these eigenfunctions, and using the initial condition we can find all the coefficients explicitly. And so this provides a formal solution of the problem. For arbitrary R we have now this at least formal result. And so here, because I think I need to cite the conference organizers at least once in this talk, so I should mention that the structure of the solution is very similar to the structure of quasi-one-dimensional problem of the nonlinear sigma model obtained in this work. Okay, so now, well, it's a formal solution, so we cannot really extract a lot of information from this complicated expansion. So what I would like to do now is to look for a particular solution, in the sense that I'm going to look now for a cubic sample so that m equals to L. And so then we can see that the important parameter which appears in the solution, so this in the exponential function there is this combination R over N, and so this combination is, so if you calculate it now in terms of parameters of the model, we will see that it is nothing else than inverse dimensionless conductance. And then in the thermodynamic limit, when L tends to infinity, clearly we have different type of behavior depending on the dimensionality of the system. For d smaller than 2, so this parameter, because of this exponent 2 minus d, tends to infinity. And in this case, so all these exponential functions will be suppressed here in the integral, and we are left just with this isolated eigenfunction. And so this limit corresponds to localized fixed point, where everything is determined by this single Whittaker function. In the opposite limit, when d greater than 2, parameter tends to 0, and that means in this case all the Whittaker functions play certain role. So and this is so that means this is a metallic fixed point. For d equals to 2, well, r over n is a constant, so it's a marginal case, and this case need to be considered separately. Okay, so now I'm going to discuss these two regimes in more details. So the first one, in the localized regime, as I mentioned, so everything is determined by this single Whittaker function. And if you want to understand the asymptotic of the solution, when n tends to infinity, we need to work out this asymptotic. So the point is that now this n enters in two places. N is an index of this function, and n also enters the argument of the function. So it's not very trivial problem, but it can be solved, and then one can show that the stationary distribution of delay times is given by this formula. So basically there are two parts in the distribution. For tau of order of 1, so there is this formula, and for tau greater than n squared, there is this tail. So this 1 over tau squared tail was found analytically before in 1D and quasi-1D systems in many works. So this different power tau to minus 3/2 was found before in some numerical simulations, in particular numerical simulations for 2D Anderson model in this paper. Okay, so now let's look at the opposite regime, the metallic regime. So this time this parameter is much smaller than 1. And in this regime, it turns out that instead of looking at this formal expansion in terms of Whittaker function, it is more convenient to go back to the equation for f, somewhere here. And one can show that in this limit, the last term can be neglected. And then we get some linear, or non-linear, but first-order differential equation. And therefore, we can solve it using the method of characteristics. And so the way to do it, first I introduce a new function psi, and so in this way, and then the equation for psi becomes just the so-called implicit first Burger's equation, which can be solved, as I said, by the method of characteristics. So this is the solution, and so it's written in terms of new function Z0, which is a solution of this transcendental equation with small function f defined here. Okay, so this solution provides works for arbitrary value of L over R, capital L over small l in the metallic regime, and then one can analyze it further. So assuming that now L is much larger than L, small l, we can find an approximate solution of this equation using some scaling. So we can scale functions Z0 and Z with corresponding powers of R, and scale our function f also in terms of these new variables, and then keeping only the leading order terms in R, we can derive a solution in this limit. So one can see that this scale for Z implies that delay times is scaled like L squared over D, where D is the classical diffusion constant. And so this is what we expect in the diffusion regime. And then, so the solution for this scale function f looks like this, where again there is some new function y which satisfies some another transcendental equation. Okay, so from this solution we can derive the result for the density. So again, scaling the density in a corresponding way, so introducing this new scaling density rho tilde, one can show that this scale density is non-zero only in some finite interval, and one can find the edges of this interval explicitly, and also one can find how the density behaves when W approaches these two limits. So in one case we get the power law behavior, and the second case the behavior is given by this expression. And for intermediate values of W, we can just find rho solving numerically this transcendental equation. Okay, so we can see again here appearing on this power law 3/2. This time it's not localized regime, it's metallic regime, and so this power law was observed before in numerical works, and actually it can be explained using some arguments involving classical diffusion. Okay, so now I would like to compare this approach with DMPK equation. So what is DMPK equation? Well, in DMPK equation, usually we consider similar situation, but we have usually two leads. The scattering matrix, again, can be written in terms of reflection and transmission blocks. And then we are interested in the so-called transmission eigenvalues, which are eigenvalues of the matrix TT dagger. And so using similar strategy, increasing the length of the sample L by delta L, one can derive the Fokker-Planck equation for the distribution of the transmission eigenvalues. So let me now compare what is the difference between DMPK equation and my approach. So okay, so the first difference is that, as I said, usually one consider here two leads. There are some exceptions which I'm going to discuss in a moment. So here is a single lead, and the objects are quite different, so this is why it's not easy to compare these two things. But the main difference is the following. When one derives the DMPK equation, one needs to make an assumption about the slice, about this slice delta L. So usually one uses so-called equivalent channel assumption for a slice. So here I don't use any assumption of the slice. The slice is treated microscopically. Instead, I use a similar assumption, but for the whole sample, where randomization happens already because the length of the system is much larger than, let's say, mean three pass. And so this is why DMPK approach is restricted to quasi-1D, while this approach should work for arbitrary dimensionality. So as I mentioned, there are a few exceptions. So when DMPK was derived for a single channel, so what was done in this works, one considered a single lead, but also includes non-zero absorption, and calculated the statistics of reflection eigenvalues. And then one can show that at weak absorption, the reflection eigenvalues are actually related to delay times that time consider. So one can make a comparison, and what one gets that for quasi-one-dimensional geometry, indeed, the equations looks very similar. So basically, there is agreement for quasi-one-dimensional geometry as one would expect. Okay, so now I'm going to discuss the second setup where I have two leads attached to the sample. Again, the same particle in the same disordered potential, but now with two leads. So this time I'm going to use closely the derivation of the DMPK equation. So in order to derive, we need in more detail about the structure of reflection transmission eigenvalues. So they can be parameterized using so-called polar decomposition. So basically, it's like eigenvalues and eigenvectors of these matrices. So this matrix U and V are two unitary matrices, and matrix capital T is diagonal matrix which consists transmission eigenvalues. So using the composition, again, composition rule of scattering matrices and perturbation theory, one can derive the change of eigenvalues. So in order to derive the Fokker-Planck equation, we need to calculate the first and second moment for the change of the eigenvalues. And this is what is done here. So here you can notice there I introduced some new objects, these coefficients, Jn. So what is Jn? Well, Jn is constructed from the matrix elements of matrix U and longitudinal eigenvectors Qk in this way. So basically it's sum over all matrix element Q, UKN for a fixed n, and then weight it with the corresponding momentum vector QK. So now, in a standard derivation of DMPK equation, one assumes that this matrices U and V just uniformly distributed over unitary group. So in this case, so U model squared is just a constant, and then in this case, one would obtain the standard DMPK equation. So if you look now at how this matrix elements looks for a two-dimensional Anderson model, we can see that now it's definitely not a constant, so there is quite strong deviation from this uniform distribution. But the good message is that if you change, so here I keep the width of the system fixed, I change the length from 30 to 480, and we can see nothing really changes here. So that means this distribution is stationary, and so I'm going now to make a conjecture about how this distribution can be obtained. So basically, the reason why these matrix elements are non-uniformly distributed is the following. So the scattering matrix and also other matrices that appear here, they all depend on this matrix that we saw already. So it's a matrix of the potential multiplied by this matrix Q. And I claim that exactly the appearance of this matrix Q, diagonal matrix Q, makes the distribution of these matrix elements U non-uniform. So I'm going to make the following conjecture, so that statistics of this U is actually the same as the statistics of the eigenvectors of the so-called deformed GUE matrix. So what I have here, H tilde, is just a standard GUE random matrix, and I multiply it from left and right by this matrix Q. And then, so what I claim is that the eigenvectors of this matrix H will be the same, they have the same statistics as the eigenvectors U in our model. Okay, so let's look just in the numerical results. So here, well, you can see that indeed they look quite similar. And if you remember, for derivation of the DMPK equation, we need actually to know these quantities Jn, which can be calculated in terms of this matrix element U. So if we compare now this Jn calculated for the Anderson model and for this deformed GUE matrix, we can see that indeed agreement is very good. But now we can use this information in order to derive the DMPK equation. But of course, for this we need to know how this Jn look like. So what we can say about Jn in the deformed GUE case. And well, fortunately, this was done a couple of years ago in one of my work. So one can, okay, so I'm not going here to go into details, but the point is that for this type of random matrices, one can calculate the moments, the local moments of the eigenvectors. And so the local moments of the eigenvectors can be found in terms of, so this is a parameter qk of our model, and also there are two parameters s and t, which appear here. These two parameters, they are solutions of two simultaneous equations that you can see here. So, and then knowing s and t, you can calculate all the moments of the eigenvectors. So for our derivation, we need just to know the first moment I1, and in principle, one can analyze these equations and get quite a lot of analytical results, quite a lot of understanding about how this coefficient Jn, how they look like. Okay, so once we know this coefficient Jn, we can just now plug in these two first and second moments into the general expression for the Fokker-Planck equation. And so this will be our generalized DMPK equation, which now will contain all information about longitudinal eigenvectors. And so this is actually where I stopped now in my research. So the next goal would be to check that this equation, for example, reproduces correctly weak localization correction for arbitrary dimensionality. So if it really works, then it will be a good sign that this generalized DMPK equation can be used for arbitrary dimensionality. however, I should add that the fact that now we have this coefficient Jn in the DMPK equation makes it quite complicated. And so if any of you encountered similar type of Fokker Planck equation before, I would be happy to learn how one can deal with such type of equations. Okay, so just to conclude, so I demonstrated you in the first part the statistics of delay times in diffusive localized regime at weak disorder. So we saw that this result predicts correct localization, delocalization transmission, transition depending on dimensionality in the thermodynamic limit. In the second part, I present you results for generalized DMPK equation. So this is work in progress. And there are many, many things that I would like to do further. So this is just the list. And thank you for your attention.